All right, guys, we are starting section 8.2, which is to learn how to graph simple rational functions. Okay, so a rational function is a function that has the form f of x equals p of x over q of x. So basically what we're saying is that we have a polynomial in the top and bottom of our function. And q of x cannot equal 0 because we can never divide by 0 because we know that that sends things off to infinity and it's undefined. So the inverse variation function f of x equals a over x. So a is a constant, so we have something simple as a number divided by x, and that is a rational function. And so we're going to talk about this when we have f of x equals 1 over x. We're going to consider this the parent function for all rational functions. This is the basic shape that all rational functions are going to take, and then we expand on it from there. So the graph is a hyperbola. It's going to have two symmetric parts. Symmetrical parts. We call these parts branches. And the domain and range are going to be all non-zero real numbers. All non-zero, meaning 0 is not allowed, real numbers. And as we've talked about before, that means that we can have positive and negative numbers, we can have decimals, we can have irrational numbers, we just can't have 0. So if we take a look at what this graph is going to look like, we are going to have a horizontal asymptote, at y equals 0. So right through here, we are not going to be able to touch that line. That's an asymptote. And then we're also going to have a vertical asymptote. X equals 0. So again, right through here, we'll not be able to have a point on our asymptote. Now, for those of you who are unfamiliar, an asymptote is a line that a curve approaches but never touches as it heads to infinity. As it heads towards infinity. So as we get really, really big or really, really small, the graph is going to get very, very close to it, but it's never going to cross it. All right, so let's go ahead and put our graph on here. So as we said, we have hyperbolas, and so they're going to get really close to it, never really touch it. And so that gives us our basic shape here. Yeah, I'm going to do a little bit better job of that. So we're actually going to come through, and when x is 1, the whole thing equals 1. So we actually are going to look something a little bit more like this. So we can be a little bit more careful. And the same thing going this way. And so this is the basic shape of a rational function. We're going to have this hyperbola. My curve isn't quite perfect. Usually we like it to be a little bit smoother, but for now that'll work. And we're going to have two asymptotes, a vertical and a horizontal, because x can't equal 0 in this case. Okay? So let's keep going. Let's take this a little bit further, because obviously there's more things than just the parent function. So when we look at the rational function in the form a over x, that a is going to change what that graph is going to look like. So in this case, our asymptotes are still going to be the same. Our asymptotes are still going to be y equals 0 and x equals 0. And then we can plot points using a table. So we could use a table on our graph, on our graphing calculator or on Desmos or something like that. So we can use a table to get a whole bunch of points, and eventually that'll feel unnecessary, but we can use a table on our graph, and we would use that table to plot points on our graph and allow us to draw the two branches that are going to go through those points. So if we take a look at this, we're going to come in here and we're going to have our asymptotes, again, going through our horizontal and vertical axes. Okay, so there's our asymptotes. And then as we start plotting points here, we could plot in points. So when x is 1, y is 4, so we know that's going to be a point. And when x is 2, we would have, when x is 2, y would be 2. And so we can see, as we were to plot points in here, we would get a nice graph here. And so we can go ahead and sketch our graph through those points. Okay, and as we already said, we know that this is going to be symmetrical, so our graph is going to look identical going the other way as well, just down here in the negative, in that third quadrant. So as we come through here and look, we can see, and then we can draw our branches as they come through. And they keep going, and they're going to get really, really close to those asymptotes, but they're never really going to quite hit them. So now if we compare the graph that we just drew to the graph that we had a moment ago, we've got this graph, and then we scroll back up and we can look at this one. They look very similar, however, they look a little bit different, right? So think about that. How are those different? How are those the same? So if we think about how they're different, we can see that the graph of 4 over x is farther from the x-axis, from the axes, actually both of them. So what we've done is we've actually stretched, we've increased the size of this graph. That's what multiplying, increasing the size of our A does. So we've increased our graph, making it bigger. And so it's further from the axes than the graph of 1 over x. It's exactly 4 times further away. But they do have the same range, the same domain and range, and the asymptotes are also the same. So we can see, even though these two graphs are different, they are very much similar. Okay? So if we take that simple graph that we just had, which is those two hyperbola pointed off in those two quadrants, we can actually do a lot more complex things with that same structure. So if we're graphing translation, so translation is a horizontal or vertical shift, we can have a graph of the form y equals a over x minus h plus k. And as I hope you've heard before, maybe when you're talking about quadratics, h is going to be your horizontal shift, and k is going to be your vertical shift. So what this means is h is going to be the vertical asymptote, so x equals h is going to be your vertical asymptote, and our k is going to be the horizontal asymptote. Where y equals k. Okay, so let's take a look at this and we'll do one example, and I think we'll call it good for today. So steps for graphing a rational function in the form y equals a divided by x minus h plus k. So we're going to start off by drawing the asymptotes. Draw the asymptotes. So x equals h and y equals k. Those are our asymptotes. So let's go ahead and put those in our example here. So x equals 3, y equals 2. Those are our asymptotes, so we'll put that on our graph. X equals 3 is our vertical asymptote, so we'll put that right here. I guess the arrows are unnecessary. We'll take those out. Here, we'll take those arrows out. It does keep going, but it's kind of unnecessary. And then y equals 2 is our horizontal asymptote. So there's our asymptotes, right? Asymptotes. So that's step 1 of being able to graph one of these. Then we can come in here and go to step 2, which is to plot points to the left and to the right of the vertical asymptote. And so using a graphing calculator or a calculator in general can make this very simple. Now, to be honest, the way I generally approach this is that knowing that this intersection of these two asymptotes right here, you're always going to be 1a away from it. So if I go to the right, one here, I'm always going to be a high. I'm going to be a high, which means that in this case my a is 1. So one of my points is going to be right here. So again, we could do a table of values, and you could put this into a calculator, x, and here's your y. And we could say, so here's 3, which is our x, is our vertical asymptote. And so if we plug in a 4, we would get 3. If we plug in a 5, we would get a 2.5. If we plug in a 6, we're going to get a 2.33. We could go back the other way, and we plug in a 2, we would get a 1. If we plug in a 1, we're going to get a 1.5. And we plug in a -1, we would get 1.75. Okay, and we're not going to have anything that shows up at 3 because that's our asymptote. And so if we take those points and started plotting those on our graph here, we would see that, again, we're going to get very, very close. So here we are. There's 4. 5 was 2.5, so something like this. 6 was 2.33. And so again, once you have one or two of these points in here, you can kind of go, oh, I know what the shape of this is going to be. Let's draw that in. And then we can sketch that in. Going the other way, again, I know that I'm 1A away from that, and then the rest of this is just going to get really, really close and get really, really close. More points makes your graph a little bit better. So that gives us our graph. So we've just done step 3, which is to draw the two branches. Draw the two branches of the hyperbola so they pass through those points and approach the asymptote. And approach the asymptotes. Okay, and so when we think about domain and range, our domain for this, domain, what x values can you put into this graph? We can put in all real numbers. Again, we'll use shorthand for this, the double barred R here. All real numbers, except, there we go, except 3. So x is not allowed to equal 3. And then our range, again, those are the y values we can get out. We can get all real numbers out again. So again, that's the symbol here, all real numbers, except we cannot get 2. There's an asymptote there. Y cannot equal 2. So that gives us our basic approach to what we're looking at here. And I think that will cover us for today.